Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. I bid to my respective panels, Dr. Ahmad Fateh and Dr. Suryana. My name is Nur Arni Munirah binti Samsudin. My metric number is AE160010, and today I'm going to present to you my final year project that entitled The Development of Solar Powered Automatic Fertilizer System in Fertigation Technology. So the theme is about enhancing sustainable fertilization practice with solar. So without further delay, let's move to the contents. So this is the flow of my presentation. I will start with the introduction along with the problem statement and objective. Next is the methodology, result, conclusion, and I will end my presentation with the recommendations for the future works. So first is introduction. Okay, during 2017, agriculture sector has contributed about 8.2% of GDP. So this has made agriculture sector as one of the important sectors in Malaysia. Modern agriculture such as fertigation system can bring positive impact in terms of yield production and also the incomes of the farmers. So in conjunction with this, farmers should actually take this golden opportunity to broaden the fertigation technology into the next level. Okay, upgradation of the fertigation system can also be done along with the renewable resources such as the solar energy. Okay, lately government has announced the new national renewable energy target, which is to reach 20% of the renewable energy penetration by the year of 2025, and 50% of it is coming from the solar technology. Okay, apart from that, Malaysia has produced high solar irradiation as compared to other country. So Malaysia has produced about 400 to 600 megajoule per meter squared monthly. Due to the strategic location of Malaysia, there is place near the equator. So this can be an advantageous actually for the farmers to implement the solar-based application system. Okay, with all the stated facts, we believe that all of these things can tackle a lot of issues that are lingering among the farmers. Some of them are including in my problem statement. So this is the problem statement. The first one is about traditional fertigation system. We know that before this, fertigation system has been done traditionally, where the mixings of the fertilizer is being done by human. So this traditional fertilization system is actually not precise, and it also could affect the growth of the plant and also bring major constraint on the environment. And the most importantly, it also can affect the human health. Okay, next is about the electrical grid supply. So we all know that most of the agriculture sector are based on the rural area. So the supply from power grid system is actually not practical to be executed in rural area due to the limited electricity accessibility. Okay, thus solar powered automatic fertilizer system need to be implemented to overcome these two issues, which are electricity accessibility and the other one is overuse fertilizer usage. So with the proposed project, here is the objective of my project. The first one is to design a PV system for automated fertilizer system in chili fertigation technology. The second one is to design a system that can automatically agitate proper proportion of fertilizer. And the last one is to develop a prototype for the development of solar powered automatic fertilizer system in chili fertigation technology. Okay, so to achieve the objective of the project, so here is the methodology that consists of 3 phases. So for phase 1, research and literature review based on solar PV system and automatic fertilizer system had been done. Next is the designation of PV system for automatic fertilizer system. So for this point, a real application of automatic fertilizer system is considered, where we choose 300 chili crops for the fertigation system. Okay. Next is phase 2. Phase 2 is about the development of algorithm for automatic fertilizer system using Arduino IDE software. What I mean by algorithm is I introduce a ratio-based control system in order to agitate precise proportion of fertilizer A, fertilizer B, and water. Okay, so I will explain it further in my flow of my project. Okay, next is phase 3. Phase 3 is about the development of solar-powered automatic fertilizer system prototype. And the last one is after all of this thing is achieved, experimental and analysis had been done. Okay, next is the flow of solar powered automatic fertilizer system. Okay, so here is the prototype for the solar powered automatic fertilizer system that consists of PV system and also automatic fertilizer system. For the PV system, it consists of solar panel, charge controller, battery, and also an inverter, which is connected to 12 volt DC adapter. So this 12 volt DC adapter is connected to the load of automatic fertilizer system, and it is going to use to supply the electricity to this system. So before I start the demonstration, I would like to tell you the flow of this automatic fertilizer system. And it all started with the input of the fertilizer A in this tank, fertilizer B, and also water tank in this orange tank. Okay, so all of this input will start flowing into the mixer tank. So this is the mixer tank. Once the relay is in normally closed condition, and it will trigger the water pump in this tank to be operated. Okay, to be specific, water pump 1 and water pump 2, which connected to the flow rate sensor. So this is the flow rate sensor. Will independently stop operating once the amount of fertilizer A and fertilizer B reach 25 milliliter. While for water pump 3, it will stop pumping the water into the mixer tank when the ultrasonic sensor detect the water level in the tank is 70 centimeter away from the tank cover. So this is the ultrasonic sensor. Okay. As you can see here, there's also a motor agitator that is used to mix the solution of the mixer tank. The solution in the mixer tank, sorry. Okay, so the speed of the motor can be regulated by using this potentiometer. Okay, next is the EC sensor. So, sorry. Here is the EC sensor that are going to be used to detect the EC value of the solution. Okay, and all of the output of the EC value are going to be displayed in OLED display. Okay, apart from that, OLED display will also display the output of the distance and also the flow rate reading of flow rate 1 and flow rate 2. Okay, so that's the flow of the solar powered automatic fertilizer system. Now we will carry on to the results. The first one is about the PV sizing for PV system. This is the assumption that I use to calculate all of the equation in chapter 3, and this is the load estimation, where it consists of 3 motor pump, basically 3 motor pump. The first 2 motor pump is used for fertilizer A and fertilizer B, and another one is used for agitator, which is used to mix the solution in the mixer tank. So this is the estimated power produced, and to calculate the energy demands, we need to multiple the total power with the hours per day. So this is the total energy demands that we are going to use later to calculate the sizing of PV components. Okay, so this is the component sizing, this is the size needed, and this is the selected size. So the overall result for this PV system can be illustrate in this figure. So we use 160 watt of power of solar panel, and then we use 50 amp solar charge controller with 100 Ah battery. And then the inverter, we choose 2k watt of inverter that are going to supply the power to the motor for fertilizer A, motor for fertilizer B, and also motor agitator. Okay. Next is about the circuit configuration of automatic fertilizer system. So the circuit configuration have been done via freezing. So this is the circuit. As you can see here, this is actually a motor pump, but since the library for water pump is not included in the freezing library, so I use motor pump to replace the water pump. Okay, so that's the circuit configuration. Here is another circuit configuration for standalone PV system that consists of solar charge controller, solar panel, battery, inverter, and so let's move to the video demonstration. Okay, now I will proceed with the demonstration of the system. As you can see here, this is the OLED display that display the output value of distance, EC value, flow rate 1 and also flow rate 2. And it is receiving the supply from charge controller. Okay, now I will turn on the power supply for the water pump and also motor agitator. So as you can see, all the inputs has going into the mixer tank. Okay. Okay, now the ultrasonic sensor already sent the constant distance, which is the 70 centimeter. Okay, it is still not constant. Okay, now the water pump 3 and motor agitator has already stopped. Since the EC value is at the standard value, then no EC mechanism, feedback mechanism is involved in this process. So that's all. Okay, this is the last demonstration for EC feedback mechanism. So as you can see, there are 3 different solutions with 3 different EC value, and I will dip the EC sensor into 3 different solutions to see the feedback of the water pump 1, water pump 2, and also water pump 3. Okay, so now let's start with the first solution, which is the water solution. Okay, so now I will turn on the supply. Okay, this is the EC value of the water. So here you can see that water pump 1, water pump 2, water pump 3 are operating and entering the motor. Sorry, entering the mixer tank. Okay, now is for the second condition. This is the EC value for, this is the EC value for the second condition, which is the standard EC value. Now I'll turn on the supply for the load. Okay, notice that there are no operation of any water pump because the EC value is already at the reference value of EC. Okay, now is for the solution 3. This is the EC value, which is out of range of the EC standard. Okay, now. Okay. The water pump is now operating and entering the mixer tank. Okay, I hope you enjoy the video demonstration. So here is the overall performance of the system based on the previous video demonstration. So in initial condition, the distance shows that it is 23 centimeter away from the cover tank, and the flow rate 1 and flow rate 2 reading is initially 0, and the EC value is 0.25 ms per cm. It is supposed to show that the EC value is 0, but since the EC sensor is not accurate, so that's why there's still a reading obtained at the EC value, even though there's no solution in the mixer tank. And here, the initial condition, once we on the supply, the water pump 1, 2 and 3 are activated and are going to feed into the mixer tank until a required condition. Okay, next is the final condition. This is the OLED display for the final condition. The distance is 70 centimeter away. Flow rate 1 and flow rate 2 are not giving the same value as it's supposed to be. This is also due to the inaccuracy of the flow rate 1 and flow rate 2 reading. It can also be due to the Hall effect sensor, and all of these things are going to be included in the report. So this is the EC value of the final condition for 0.17 millias per cm, which is the standard value. So there's no EC feedback mechanism needed, and the water pump 1 and 2 are off when the flow rate 1 and flow rate 2 more than 25 milliliter. Okay, next is the EC feedback mechanism for the second part of the video. So there are 3 conditions. The first condition is when the EC value is less than 2 ms per cm. And what happened to the water pump? The water pump 1, water pump 2 and water pump 3 will on. And next is for the condition 2, when the EC value is between 2 to 5 ms per cm. The water pump 1, water pump 2 and water pump 3 will off, since it is in the standard EC value. And the last one is condition 3, where the EC value is more than 5 ms per cm, and water pump 1 and water pump 2 will off, as it detect that there is excessive fertilizer in the mixer tank, and the water pump 3 will on to stabilize the EC reading back to it normal. So after the solution reach the standard value, then all of the water pump will be off. Okay, next is the conclusion, and all objectives of this project are successfully achieved. So from objective 1, PV solar sizing for each component are properly calculated by considering the load requirement. And for objective 2, from the developed algorithm, the circuit of automatic fertilizer system is able to run accordingly. And objective 3, implementation of hardware is a success because the PV system is able to supply electricity to automatic fertilizer system. So as the conclusion, the proposed prototype is able to provide a better management for the fertilizer system by reducing the manpower and human intervention. Okay, next is the involvement of renewable resources such as solar power in this project can provide a great solution to tackle the electricity accessibility problem. Okay, now we have come to the last part of this presentation, which is the recommendation for future works. The first one is about to develop a fully automatic fertilizer system that consider the parameters such as the sand moisture, sand pH, humidity and surrounding temperature. So by implementing a fully automatic fertilizer system, I believe the system are able to increase the performance of automatic fertilizer system. Okay, next is to implement a solar monitoring system in order to get a continuous power supply for the fertigation. Sometimes the solar system is not giving the highest power due to the presence of unwanted particles such as the dirt, shading, and also the dust. So by implementing a solar monitoring system, we are able to get a continuous and prolonged power supply for the fertigation system. Okay, next is to design a user-friendly GUI for the automatic fertilizer system. Okay, user-friendly GUI is very easy to the farmers so that the farmers can choose which easy value that they want. Okay, next is to use a high quality sensor. Okay, this is very important in order to enhance the performance of the system. As you can see, my system is not very accurate due to the quality of the sensor itself. So by using a high quality sensor, I believe that the performance of the system can be increased. Okay, last but not least is to add on another 12 volt 4.5 Ah battery bank to the solar system to increase the storage of the supply. So that's it. That's all from me. Thank you.